Hi, welcome to this session on STM32 bootloaders. So I have split this session into two or three parts where we will ultimately try to flash the STM32 using an external Wi-Fi enabled chip to enable firmware over the air updates. But in the course of the journey, we need to cover some fundamental concepts like what is a bootloader and how the bootloader is able to jump to the application space and how we are going to configure the project to have a bootloader and what are the internals of a bootloader. Okay, so we are going to cover all this, and as usual the code and the session notes are present in the description. So this session happened on January 25th 2026. This is just a recording. Okay, so very important, you should understand that bootloader is not just for flashing the application. It is a powerful initialization tool that helps you to recover. So this boot happens during the reset phase, right? So we are going to see what are the uses of the bootloader, how we configure the bootloader, and how we are going to write a bootloader, and what features are the STM32 and the ARM Cortex architecture have in store to enable this feature. Okay, so we'll meet you in the next segment. Okay, so I am assuming that you have gone through the previous video, which is the bare metal STM32 bare metal session with no HAL, no libsimsys. So there you would have seen this concept called vector table. Okay, so basically let us understand the ARM Cortex-M standards and the facilities that are provided to in order to enable bootloading. First, the ARM Cortex standard says that we need a vector table structure, an initial MSP value or the main stack pointer value, the reset handler, and the IRQ. So this is called a startup sequence. So whenever you write a startup.s, you will take care of these four. Okay, the main stack pointer, the MSP, is where the application starts from. Okay, so it holds the value of the reset handler. Okay, and the reset handler is the address in memory or the function pointer that is invoked when you press the reset button. And whenever you have an interrupt in your application, that interrupt is handled by the IRQ handler. Okay, so very important that the startup sequence consists of a vector table, the initial MSP value, the reset handler, and the IRQ handlers. Okay, now the Cortex has two modes of operation and two privilege levels. Okay, so if we see the Excalibur whiteboard, so there are privilege levels. Privilege means how much of access you have, that is called a privilege. There are two privilege levels. One is the unprivileged level, where you have restricted access, you cannot use certain instructions. Okay, and next you have a privileged access where you can use all instructions. You have you can also use the system control instructions. Okay, and you can modify the critical registers. So generally, if you want to do something that is related to the system, or you want to change something like moving vector tables, you need to go into the privilege mode. Okay, when an application is normally running, it will run in something called as a thread mode. In thread mode, it only has unprivileged access. But in a handler mode, like when you enter into an interrupt, it will have both unprivileged as well as privileged access. So we can just call it privileged access for short. Okay, so in thread mode, you can only do certain things like run your application. Okay, and maybe copy stack pointers here and there, but that's all you can do. But in a handler mode, when you are servicing an interrupt or the sysdig, or you are trying to come out of a hard fault, or you're trying to come out of a trap condition, you will have special privileges. Okay, like the ability to reset. So this is what we need to understand first: thread mode, handler mode. Thread mode, is for the normal mode of operation and you run in an unprivileged access. In handler mode, you have privileged access. Clear? Now, why this explanation matters? Okay, so we need to understand that the bootloader relocates the vector table. Okay, very important. These three things. The bootloader relocates the vector table, jumps to the application, and reinitializes the main stack pointer and program counter correctly. If you do not understand this, your application will jump, but it won't run. Very important. Three things. Okay, so first we will understand how the flash is there and how we are going to write our linker file and startup file accordingly. Okay, so more details you can find in the notes, but let us go to the blackboard and go for a session where we understand in detail. Okay, I will start with my problem statement. My problem statement is I want to write a bootloader that fits within 8 kilobytes that can jump conditionally to two applications, application 1 and application 2. Okay, now the reason I have this is because on a blue pill you have 64 kilobytes of flash. Some variants you have 128 kilobytes of flash. That is okay, but it is very important that you make a partition. Now, what a partition is? A partition is a section in flash memory that contains data, code, entry point, and vector table. Very important. A partition is a section in flash memory that contains code, data, entry point, and a vector table. Now, if you have an application that sits alongside a bootloader, then definitely it can't share the same space as boot. All right. So you have to partition or set your memory space accordingly. And how granular can you make your memory space? 1 KB because of the page size restriction. There are 64 pages of 1 KB each. Okay, let me write 64 pages of 1 KB each. Therefore, you have to play with this boundary. So 8 pages you will give to your bootloader. The 28 pages you will give to one of your application 1, and the next 28 pages you will give to your application 2. Sometimes this page granularity might vary, depend on the microcontroller and flash, but for STM32 the flash page is 1 KB. And anyway RAM is shared, so when in boot the entire RAM region is used, and when the application jumps, again the entire RAM application is used. So there is no reason to partition my RAM. Okay, unless I'm doing multi-core or RTOS, or if I need a dedicated buffer in RAM for something, there is no need to partition my RAM for now. Okay, now in this section we will see why the partitioning is needed. If you see your RAM, our RAM starts at this address and ends at this address, 20 KB. You can find this information in the STM32 datasheet. I will show that also. Okay, so if you take your application, the way you are going to make sure is that the vector table and the stack pointer are clearly defined. So how many applications do you have when you have one bootloader and two applications? The boot is also an application. Hence, in total, you have three applications. All right. Now, your boot will start at a certain address. Okay. And 8 pages after that, your application should start. Therefore, the start point, okay, or the stack pointer will change accordingly. And similarly, the vector table will also be shifted by that equal amount. Similarly, the application 2 will be shifted by both the size of the boot and the application 1. Here we can see that graphically. My boot is starting here. This is the linker file. My boot is starting at this address, let us say. Okay, 8000. Okay, and my stack pointer will point exactly there. Now, my vector table will point 4 units later, 4 bytes later. Why? I will come to that in the linker file and the startup table. But just remember, immediately after 4 bytes at this address, you will have your vector table jump. And I told you, when you have an application that is sharing the space along with the bootloader, you have to move it by the size of the bootloader. Here, my application is shifted. If you see the linker file for the application one, this is the linker file for the application one. The origin of flash, see, the RAM sections will always remain the same. Okay, but the origin of flash will change. Okay, so if you see, this is the bootloader details. It starts at 8000 and the size is 8K. Similarly, for application 1, it starts where the bootloader left off and the length is 28 pages, 28K. Okay, similarly, for application 2, same story. Okay, what happens? You start by adding the size of both the boot and the application. Okay, so this is how you set up the linker. The linker file will tell how much memory to allocate and where in flash should the hex file sit. Now, based on this information, we can start writing our applications. So this is the initial memory or initial memory layout and the mental model that you should have. Okay, see this video multiple times. Okay, as it becomes clear. Okay, and remember, here I didn't discuss much about stack and heap, but if you have a heap, you remember that you have to allocate accordingly in the CubeMX, and similarly stack will grow from the end. Therefore, one most important variable is end of stack variable. End of stack is nothing but where your RAM is. So if you want to know the boundary of your RAM, this end of stack variable is also defined. Okay. So in the next segment, we will see and deep dive into the code and understand how our idea or our partitions translate into the application and bootloader code. Okay. Okay. I have the reference manual in front of me and I have opened the different boot configuration modes. Out of this, we are only going to discuss the main flash memory boot space because our bootloader is sitting as part of a main flash memory. Therefore, if your boot pins are at any other positions apart from this one, your application won't boot. That is why we are calling it a custom bootloader. The STM32 sometimes come with an embedded bootloader in boot 11 position. Okay, so if already there is an inbuilt embedded bootloader that can flash your application, okay, it sits outside the main flash memory space, therefore it has access to the entire flash. Unlike our bootloader, which is eating 8 pages of memory, this bootloader has entire access to flash and can also work in various modes like DFU, USART, CAN, etc. But the thing is, you have to physically set your boot pins this way, and it's not fun. You don't get to learn how the bootloader is working. This is also fine. It has its application. Therefore, we'll call it a custom bootloader. All right. So one thing we know that custom bootloader is taking some of our main boot space. Hence, we need to understand how the vector table works and how it is moved. Now let me go to the vector table. Now, if you see the address of the vector table, let me remove myself. If you see the address of the vector table, it starts from 0. Okay, which means that the reset handler is 4 bytes away. That is the next address. So the moment you click your reset button, this reset handler will be invoked. Okay. Therefore, it is very, very important that if your bootloader is present in Flash, you have to move this address for the application also. Remember, there are three sets of applications. So when you have three sets of applications, you will have three stack pointers and you will have three sets of vector table. The first vector table will be default. It will start where it needs to, here. But the next vector table, you need to shift it by the size of the boot. And the next vector table, you need to translate it by the size of the boot plus application. Okay, it's very important. Otherwise, if you have interrupts within the application, it will jump into the flash address where the boot is present. You don't want that. When you have three vector tables, the application must use the vector table assigned to it. Clear? Now, the way this is done is using the vector table offset register. Now, where it is, we will see. Might be in as part of the system registers, but we will see it. Okay, so it is not in the reference manual. Instead, it is in this page, the definitive guide to the Cortex-M3 edition. So if you read this book and if you go to the page number 131, where it deals with the vector table VTOR. Okay, so in order to move to a new vector table, there is a ARM Cortex control register SCB, system control block. Here you have the VTOR register. The moment you set this, okay, your application will recognize this as the offset to the new vector table. Clear? So more on this you can find in this very beautiful book, the definitive guide to ARM Cortex, and it is the basis of some of the chapters in my notes also. You can find this online. Okay, so next we will go to the various boot modes and how the bootloader is actually coded. Okay, now that our mental model is clear, let us walk through the code and let us understand how the bootloader is written. Let me just open code space. Okay, so this is how the organization is done. So let us see. I have my applications 1 and 2 and a simple bootloader. So let us first see how the bootloader is written. Now the bootloader has been generated from a CubeMX configuration. Okay, because I want to make use of HAL, it makes things easier. After I know what I'm doing, I will move it to bare metal. But initially, HAL makes things fast. Now let us see, CubeMX is taking some time to open. But in the meanwhile, I can open the bootloader. And that's it. I have a port for just my debug, just to print out to see what is happening. But later in the part 2, I will use this same port to start my flash loading. Like whatever data you send, that will be written into the flash. Okay. But for now, I enabled my PC13, which is the default LED. Okay, system core is enabled. This is in serial wire mode. You can disable it. That's fine. And I am using the crystal or ceramic resonators on the board. On the blue pill, generally you have both of them. Okay. And in GPI, I'm using PC13, and in connectivity, I'm setting UART to 115200 baud rate, kilobytes per second. Okay. In 8N1 configuration. That's it. So my applications are also stemming from the same CubeMX configuration. Therefore, one CubeMX configuration is fine. You can just copy it. And there's no hard and fast rule of what you can put in application 1 and 2, as long as they are fitting in the 56 remaining bytes boundary, that is 28 and 28 each. Okay. I don't want to make any changes for now, but let us see the deinitialization and jump. Okay. So first thing that I said, that we will set the stack pointer. Now the stack pointer starts where the application resides. Okay. For boot, this is the default start of flash. Therefore, we don't need to mention. But if you're jumping into any particular application after a deinit, sorry, you need to mention this. Similarly, the reset handler is the next. How do I know the reset handler is the next? If I look into the startup file, okay, the reset handler comes immediately after the stack pointer. Okay, therefore, I will set this 4 bytes later. Okay, next, I will just check if my stack pointer is in a valid address. I will disable all interrupts. Then I will clear any pending interrupts. This is most important. And I will deinitialize any peripherals that I otherwise would have initialized. See, it's very important for the proper working. If your boot initializes some peripherals which the application does not need, your application start with that peripheral initialized. Therefore, you should not make any assumptions. You should de-initialize any applications or any peripherals that you might initialize. And after you've done that, the most important step, relocate the vector table to the new application base. Okay. And then you set the main stack pointer to the application stack pointer here. After that, the jump doesn't take place. Where you have to jump, you create a reset handler. The reset handler is this one, 4 bytes after the stack, and then you create the jump. This is app entity is just a type define for the pointer of void star void type. Okay, it is just a type define, but this allows you to create a function pointer and then jump. So this is the actual jump that takes place, and there is a small menu that the bootloader runs. So whenever the bootloader runs, it shows a menu like this. Can run application 1 or run application 2 at the corresponding address. So initially, this bootloader will wait for your input. There's no default application to jump to. Since don't use this for production, this is just for educational purpose, but you get the idea. And as for the application themselves, they can be anything. I just copied the same code and shifted and removed the bootloader functionality, and I just had a basic LED blink. Okay. So if you see application 1 and application 2, it's just a copy, but these functions are not being called. All it does, it says I'm loaded. Similarly for application 1. Okay, it's just a copy and it says application 1. I can safely delete this two things because these are copied from the bootloader. But the most important thing to remember, the why I left them there, is you can do multi-stage bootloading. Like you can boot into application 1 and then boot into application 2 from application 1. That is also possible. That is why I left the feature there. So you can do single stage bootloader, a multi-stage bootloader where there's a primary and a secondary bootloader involved. So most important thing is to understand this sequence. deinit and jump sequence, and why we are doing it, and the purpose of creating the three vector tables. Okay, if you understood this, then the bootloader is in your hand. Next segment, we'll see the flashing, okay, and the demo. So you can go to this root directory of each of the projects and you just hit make. Okay, the application will build because there is a make file involved. And moment you make it, okay, you should be able to see the build directory with the hex file. Okay, this is dependent on how you set up, but mostly you can just go and do make clear clean and then say make, application will be built for you. Okay, but the most important part is flashing. The way you flash is you invoke your htflash command. Okay, so you just open a terminal, rst. So just see how the flash command is. You say htflash and then you path to your application and then the starting address vector. Most important thing is you need to follow this order. First you flash your bootloader at 0. Next is you flash your application 1 at this address. Afterwards you flash your application 2 at 9000. Okay, this is the order of flashing. Once you've done that, hopefully your board should reset. Okay, you can close this and you can go open a terminal with a serial port and just click on reset. Okay, there's some junk data appearing right now because it's not reset properly, but once you set up your serial port connection properly with the proper wiring, you should be able to do it. We'll see the demo shortly. Okay, after fixing the wiring, we can see the bootloader application come. We can just check it again by resetting the chip. Okay, you see the menu again, and if you say 1, it says application 1 loaded. You can reset it and you can say 2, application 2 loaded. So it's simple if you know what you're doing, and if you're just careful about your wiring and linker files and building. If you do it in the exact order, you can replicate it. Okay, all the best. In the next session, we will do a flash loader where we will be writing into the flash. The bootloader will take bytes from our hex file on the PC, and a script will talk to the UART and we will write the bytes to the flash and jump. Okay, so that will be a proper flash loading bootloader. Okay.